The final thing to consider when doing rotational dynamics is our main formula for linear dynamics was the sum of all forces is equal to system mass multiplied by acceleration. In rotational dynamics, we have an equivalent formula, except this time, instead of just looking at forces, we need to look at torques. Instead of just looking at mass, we need to look at rotational inertia. And instead of looking at linear acceleration, we're going to look at angular acceleration. This is expressed in the formula as shown here. Net torque equals I multiplied by alpha. Or instead of net torque, we can say the sum of all torques equals I times alpha. There are a few things to consider when using this particular formula. It can be a little bit more complicated than FMA because there may be a few more calculations that you might have to do in a particular situation. The first thing you're going to do when using this formula is determine each individual torque that is acting on your object. Don't forget that means you may have to use the formula torque equals R perpendicular with F. And so you might have to do that for one particular force acting on the object and its distance from the pivot point, and then maybe you have to do it again for another torque, a third time, a fourth time, depending on how many things are trying to rotate the object. Next, you're going to take all of those torques and add them together, keeping in mind that your counterclockwise torques should be considered the positive direction, and your clockwise torques should be considered the negative direction. Now, if we look at the formula up above, what I would usually do when we did FMA is I would do plus and minus, and then I would list my positive direction forces and my negative direction forces. And I can do the same thing here for the sum of all torques by looking at the positive direction torques and the negative direction torques, and then putting those all together. Step 3, you will need to take into consider rotational inertia, otherwise known as the moment of inertia. In some problems, the moment of inertia will be given to you. In other problems, they may simply give you the mass of the rotating object, the radius or length of the rotating object, and then a formula would need to be found, or it would be given to you, on how to calculate the rotational inertia of that object. As a side note, in your MP, there's a problem where you're going to have to do this. They give you a disk. Any disk is going to be considered a solid cylinder. Remember, the height of the cylinder doesn't matter when you're doing rotational inertia calculations, so the height of the disk won't matter, but you will need to use the formula I for the disk equals 1/2 mr squared. Once you get that calculation, you can plug it in for I. The final thing you might need to do is calculate the angular acceleration of an object. In that case, you might be given a starting angular speed and ending angular speed. There has to be a change in order for there to be a net torque. And then you subtract those, divide by the amount of time that angular acceleration occurs for, and now you can calculate the value for angular acceleration. So a few extra steps that you might need to consider when doing this particular Newton's second law, as opposed to the linear dynamics version, which itself was tricky when we first started doing it, but didn't necessarily have as many steps as this does.